Welcome back to this course of chemical crystallography. We have learnt about the data collection and data reduction methodologies in previous couple of lectures, and today we will start trying to understand how one can solve structures using different methods. So what we have done till now is we have learnt how to do a data collection. So we should start with a crystal. We collect about 20 to 30 images using a diffractometer. And then utilize the reflections obtained in those 20 to 30 reflections. Maybe it will have 50 to 200 reflections. We try to index the diffraction pattern. So index the crystal and get the values for the cell dimensions, that is A, B, C, alpha, beta, gamma, and eventually we can calculate the volume. And then based on the values of alpha, beta and gamma, we can identify what crystal system and what Bravais lattice it belongs to. So then we do a data collection strategy. Based on the Laue symmetry of the lattice or of the crystal system. So then we collected data which might take anything between 30 minutes to few hours, maybe even up to 12 hours, depending on what kind of crystal it is, how much is the volume, what is its diffraction quality, how much exposure time you are giving, and so on, and how much of data that you need to collect. Because as we know, for triclinic we need to collect much more amount of data compared to the orthorhombic or cubic systems. So after this data collection, in previous few lectures we have learned how to do a data reduction. And extraction of the IHKLs from the observed data, and also it completes the data reduction with the space group determination as well. So when we have determined the space group, we must know, we then identify whether it is centrosymmetric or non-centrosymmetric. Crystal structure. So now what we have in this data is just the values of IHKL. For all the reflections that we have collected, we just have the intensity. And as we know, this intensity IHKL is proportional to the square of amplitude of the structure factor. So this intensity can be converted to the structure factor amplitude, that is the FHKL, by taking a square root of IHKL. But in that process, what is missing is the information which is there in F. The FHKL is a combination of mod of FHKL, that is the amplitude of the structure factor, and the phase information. So the structure factor FHKL has two parts, the amplitude and the phase. The amplitude of structure factor comes from the square root of intensity, but information for phi, the phase, is missing. So this problem that we now encounter is called the famous phase problem in X-ray crystallography. So what we need is, we need to determine these phases for each and every reflection to be able to correlate the structure factor with the electron density. So we know that FHKL is related to rho xyz by a Fourier transformation. So to get this expression for FHKL, what we have is just the mod of FHKL, and which comes from the intensity, and what we don't have is the information on phase, phi HKL. So the structure solution program has to work in a way to get the phases for each and every reflection that we have measured, and then only we will be able to do this Fourier transformation effectively to get the value of rho xyz, which corresponds to the atom coordinates located at different locations in the unit cell, and as a result we will be able to determine the coordinates, suppose, of this particular molecule which might have crystallized in a monoclinic unit cell, but we don't know the bond lengths, bond angles, torsion angles and all that. You see, this is a highly complicated molecule with lots of flexibilities, and this molecule crystallizes in some space group, and one wants to determine the cell dimension, and then one wants to determine its actual structure, which means we want to determine the rho xyz at every such atom locations. And to do that, what we need is the expression for the structure factor FHKL, which should have both the amplitude and the phase information together. So in the past, there have been a large number of attempts to solve this phase problem in different ways. The most efficient way of solving this phase problem on today's date is a set of methods we call together as direct methods. Which are combination of different individual methods, which we will discuss one by one, a few of them, and then these applies to most of the structures of small molecules. One may ask, what are small molecules? These are all kinds of organic, organometallic, inorganic molecules of small size, having a decent unit cell, like a small unit cell up to about 1 lakh, 1.5 lakh cubic angstrom volume for metal organic frameworks, to compounds which has volumes like a few hundred cubic angstrom, like sodium chloride, which has a volume of about 250 cubic angstroms. So these range of molecules fall in the class of small molecules, and direct method is the most useful method in determining their structures. The other method which was established much before direct method is the method of heavy atom. So this method is named after the name of the scientist Patterson. So it is called Patterson's method, which is based on the presence of a heavy element in the lattice. So we will discuss these two methods one after another in these coming few lectures, and then we will be able to understand the structure solution that happens so quickly now on a computer, as we have seen in one of those presentations in a lecture. So what we know about X-ray diffraction? From Bragg's law, we know that the constructive interference happens when the diffracted intensity, diffracted beam, has a path difference same as the integral multiple of wavelength. So when the path difference in the diffracted beam is integral multiple of the wavelength, you get a diffraction. So now, suppose if we have set of HKL planes as I am drawing, and the atoms that we are trying to locate are placed very close to the plane that we are trying to probe with the X-ray beam. So in that case, when we have the X-ray diffraction to occur from such planes, the incident beam and the diffracted beam are, I am drawing them like this. So the distance here, if I write it as dHKL, the intensity of these diffracted beams, I write it as IHKL. There may be a situation where the atoms that we are trying to locate are significantly away from the concerned planes. The way I am drawing it is somewhere in between the planes and not exactly on the planes. So once that kind of situation happens with this particular set of HKL, which I want to write as the D H prime K prime L prime, where the intensities are also I H prime K prime L prime. So there are two situations side by side. In one case, the atoms are very close to the plane of diffraction, the plane in concern, and in other case, the atoms are far away from the planes in consideration, and from both the planes, the diffraction is occurring. So what would happen, what would we see is that the intensity of HKL, that IHKL, would be greater than I H prime K prime L prime, because the atoms, the scattering centers, are far away from the plane of this particular diffraction. So this IHKL can be represented as simply IH, and the other one can be represented as IH prime. So for two different reflections, two different sets of planes, these intensities will be largely different. So our aim is to compare the diffracted intensities from different set of planes and try to find relationships between them, and we will try to see if we can get to know the phase of one such reflection, whether can we get the phase of the other reflections of either another large intensity or another small intensity peak. So, a large value of IHKL would mean that the atoms are close to the plane HKL. So in that case, if we try to write what is the value of FH, is equal to mod of FH e to the power I phi h. This quantity phi is my phase associated with that particular reflection. So which can also be written as the sum over j equal to 1 to n fj. Suppose there are j different atoms at different places, say to the power 2 pi I h x j plus k y j plus l z j. Therefore, a large value of mod fh would mean that the atoms are close to the plane H, that is HKL. If we consider the electron density as a superposition of density waves, parallel to the lattice planes and corresponds to the amplitude Fh, and the respective phases are phi h, then we can write the normalized structure factor Fh, which is corrected for the thermal motion and brought to an absolute scale by the method of Wilson plot then the scattering factor F of an atom, the scattering factor of an atom F of an atom F decreases with sin theta by lambda, then the expected intensity of any reflection is given by mod of Fh square over the entire theta is equal to sum over j equal to 1 to n Fj square, which is a function of theta. Now the reflections measured over different values of theta cannot be compared. Directly. So we need to incorporate the normalized structure factor. As the EH square, which is equal to mod of Fh square by sum over j equal to 1 to n Fj square, where EH is the normalized structure factor. So now if you compare the equations 1 and 2, we can write that the expectation value for EH square is equal to 1 for all the values of theta. It is independent of theta. So one can write EH as equal to 1 by sum over j equal to 1 to n Fj square with a square root here into sum over j equal to 1 to n Fj exponential 2 pi I hxj plus kyj plus lzj is equation number 3. If we assume that this is a structure which contains only one type of atom, then all the Fj's can be written as Z into F, that is all atoms being same. So then in that case we can write EH equal to 1 by n z square f square with a square root on top into zf sum over j equal to 1 to n exponential 2 pi I hxj plus kyj plus lzj. Is my equation number 4, and on simplification what we can write EH is equal to 1 by square root of n equal to into sum over j equal to 1 to n exponential 2 pi I hxj plus kyj plus lzj. So the maximum possible value for the mod EH is nothing but it is equal to n by square root of n, which means is equal to root n. So from using this expression we can write the expression for unitary structure factor, that is UH, as mod UH is equal to mod FH square divided by sum over j equal to 1 to n Fj, we write it as equation number 6, and this mod UH varies between 0 and 1 as the maxima and minimum, or rather I should write varies as minima and maxima respectively. So combining these two expressions for unitary structure factor and the normalized structure factor, we can write the EH square is nothing but n into UH square, or UH square is equal to 1 by square root of n, mod UH equal to is EH. So in this part of the lecture we have tried to understand how one can derive some expressions related to the structure factor, and we can use normalized and unitary structure factors in future classes to see how these can be utilized to get the phases of unknown reflections.